Hi, my name's Bob Greener and I'm a volunteer with the Martin Fleischmann Memorial Project. So today I am going to talk about the Tree of Life Part 2. I lost a day that I was going to do this presentation, so I've tried to put something together for you in the last several hours. I'm sorry if it's not up to my normal standard, but I didn't really want to leave it any longer because I think I have to get this out before I can move on to other things. And I see Alan Goldwater has joined us in the house. Hi, Alan, and all of the others that are with us. I'm very sorry, Alan, I haven't overlaid on every image Magic Sound Lab, but I can tell you many of the images, and I'll point them out in this presentation that we are going to refer to, were only made possible by Alan Goldwater's Magic Sound Lab. So thanks again to his gracious kindness in allowing the use of his scanning electron microscope with EDS. Okay, so let's have a look at the slide here. What am I showing you when I am showing you this slide here? Does anyone know? I think I've got a comment in here from Alan about the meaning of Kepri. Yes, well that's good. We'll have a look at that at some point. In fact, this is an alternative image from an image that was on slide 55 in O-Day, which I will share with you later. And it was interesting because I put the comments in there and what I thought they meant before I actually came across the conclusions of the work of Matsumoto, and I think when you compare the two, you'll find it's quite amazing. And whether there's really anything to it, I don't know, but it's a little bit interesting. Now, what are we looking at here? Well, this is one representation of a group of symbols. And I don't know what all of these means, but this is the scarab in here, in the middle, and we'll talk about that later, what that means. And down the bottom here, we have Ka, which is the symbol for spirit, and in my view, spirit energy. And this was also on that libation disc, if you recall, from the Monopole Clutch video, and it's in the Metropolitan, I believe, that particular libation disc, which may be up to 12,000 years old or so. It's very, very old artifact, and the car, the part of the spirit, is held round the ankh, which I've indicated may be possibly a symbol for the key to all the hidden knowledge. Now, this symbol up here, take a guess what you think it is. When I look at what the Egyptians are doing with their carving, I don't think anything is a coincidence. I think it's absolutely done for a very, very specific, well thought out reason. And this up here is, in my view, the symbol of the sun, or potentially the black sun. And when I see these, I see each alternate one higher and lower, higher and lower, and higher and lower. And having been a sculptor, when you're trying to represent things in 3 dimensions, sometimes it's a little bit difficult to get that across when you're just doing a bas relief like this particular image is. And so when we've got one higher and lower and higher and lower like this, are we actually looking at something that is in the same plane that's being carved, or are we looking at something where we have 2 that are in the foreground and one that's slightly in the background, and so maybe it's trying to give a bit of perspective? And if you know the structure of the underside of the wing of a scarab beetle, they have these chitin little spikes that come down, and chitin is piezoelectric. We've discussed that with the cat hair, and the fact that that is also piezoelectric. In fact, it was one of the first things that allowed humans to explore electricity, even before we understood about electrons and so forth. And so it's made of chitin, just like hair, and it actually has these hexagonal cells. And I will do a completely separate presentation on that. I've done a hell of a lot of work about 3 years ago on that aspect. But if you imagine you've got 2 hexagonal cells in the foreground with their spikes coming up, then if there was an hexagonal cell in the gap between the 2 in the foreground, that would be a little bit lower down. So maybe what we are looking at here in this spiky thing here is actually a spike in the foreground, in the background, in the foreground, in the background, and it's representing the spikes that would be coming out of the hexagonal cells in the underside of the wing shell wing cover. There's a specific name for it, I can't remember it offhand, on the scarab beetle. And if you imagine you have, if you look at what we did with the Vega experiments, what was very clear, and you can go and look at the videos, if you have a sphere that has the minimum surface curvature, as does a torus, and that's why you get these structures in Tesla sort of experiments, and that allows for the maximum buildup of a amount of static electricity, whatever that is, to the point without a discharge. And if you want to force a discharge, what do? Well, you put convex, not concave, but convex features on that, and the more convex you go, it ends up being a spike. Okay, and a pyramid itself, for instance, has convexity on the outside edge, but then the convexity of sum of all convexities is the point at the top. And if you were to pull that down into a spike, you end up with something that's very similar, and you can go and look at this, to the field emission and thermionic emission point of a electron beam emitter from a scanning electron microscope. So you can see how all these things tie together. And if you actually look at some of Ken Shoulder's work, he has, I think, an array of spikes for producing exotic vacuum objects. And if you go and look at the 2013 patent from Lockheed Martin, they suggest, I believe, from my memory, that a similar kind of thing. They talk about one, but then there would be an array. So are they just copying the underside structure of the beetle, the scarab wing? And if that is the case, and if this is actually representing these spikes, and this is the 3D structure representation in a 2D bas relief, it could be that the Egyptians are telling Ken Shoulders and the Lockheed Martin people exactly what to do to produce exotic vacuum objects from the peak of these structures, and that when you have a whole collection of these can form coherent matter in the form of a it couldn't be not able to see it, or it couldn't be there as coherent matter, ball lightning, but whatever. And so the chitin, if you vibrated that chitin with sound, then you could create the piezo effect and maybe build up something, electrons, and they would be emitted from the spike. And if you look at the work of Messias, he found that spikes were very, very good at producing ectons, and ectons are the same as EVOs, are the same as micro ball lightning, are the same, all the same thing as also was worked with by Takaaki Matsumoto as itonic clusters. And so I believe quite possibly that the underside of the wing of a scarab beetle has absolutely everything that is necessary to create a large number of micro coherent matter exotic vacuum object structures. Now, we know from John Hutchison, these things do not have to be occurring at absolute zero, or they can occur at room temperature. And I will go into, as I said, in a separate presentation, very specific things about the beetle's wings and what time of year that they fly and how that is relevant to the ability of them to potentially leverage this technology, which is just a feature of nature. Okay, so we are going to look over, I don't know if you took some time today to go and look at the presentation that Slobodan Stankovic gave at ICCF 22, but he talked about analysing this carbon rod, this graphite rod in fact, and looked at all of the elements that were minor impurities in there. And one of the things that he found was that there was no sulfur and chlorine. And so if you take how do you get sulfur when you're doing an HHO exposure to graphite? Well, we know from ball lightning, and we discussed this before, that if you get 2 oxygen 16s, that can make sulfur 32. And I also referenced in Tree of Life Part 1 that was observed on the 10 yen coin. And here is that observation for you again, for those that may not have seen it before. So here is this section of the 10 yen coin. You can see these scalloped out areas, which I believe are part of a larger, much larger coherent matter plasma structure. And here is a classic sort of Evo strike with material eaten out, and copper tends to go away in these things. And if you go and look at the video that I shared last week, in fact earlier this week, of Savatomova's preview to her ICCF 2023 presentation that she should be giving in a week's time, or a little over a week's time, I think. She also observed the disappearance of copper, and I believe there's reasons for that, and we're going to be discussing that also with reference to the Vega Valley from the Vega experiments. But anyway, the area that we're actually looking at is this area here, which is one side of one of these kind of what I call pretzel structures. You've got the tail down here, you've got the little bit up here, and you've got the 2 sides here, that very different sides. But this area here we've blown up here, and on this area, when I was looking at this at the Magic Sound Lab, I observed these things running around on the surface, and when I went in to analyze them, I found they were little snowballs, and they were growing, starting little small, and they were making their own channels and getting bigger and bigger and bigger. And you know, this could seem amazing, but when you know that Bogdanovich saw these plasmoid-like structures moving around on his metal after plasma flow discharge, about 2 days after the experiment, glowing on a piece of metal in free air, it's not surprising to think that there could be exotic vacuum object or coherent matter that is able to stay in that state and consume matter. And what it's doing is it's taking the oxygen off this surface. And if you look down here, if you look at minor 101, minor 102 here, minor 104, wherever it is, 104 here, and minor 106 over here, these all have sulfur in them. And you can see that the oxygen is lower than the peak on this fleck. This fleck is actually got some high concentration of zinc in there. So this is a piece of zinc that's come off the other surface here. So this is the actual 10 yen coin, and I'm saying that this is the yin of the yang, or the yang of the yin. This is one side of a large coherent matter structure, and we are looking at this area over here. So when we go and look at the work of Slobodan Stankovic in a little while, you'll see that he observed the production of sulfur, and I believe that that is what we are also observing here. Okay, so when we look at other experiments that we did with the Ohmasa gas, we took this piece of titanium, exposed it for a short period of time to Ohmasa gas, and then we touched it onto this polytetrafluoroethylene, which is basically carbon fluorine polymer. And that caused an explosion, and you can see the explosion on film, and that caused this large amount of titanium to basically be blasted out, and the actual PTFE cut into the titanium here, and you can see the effects of the blast on the titanium, on the PTFE here. But what I'm going to zoom into is, firstly, this bit here is actually high. It's basically like a piece of PTFE. And what happened, and I will share this data, it's not been shared yet, but there's like a plasmoid that came in, and then it turned a corner, and then it kind of exploded. And there's all the elements you typically get from sort of plasmoid interactions or microball lightning interactions with the titanium and the fluorine in here. With the very interesting thing is, it's not just fluorine, it's fluorine and alpha conjugates of fluorine, and it's wonderful because you get things like sodium 23 and so forth. And so that's going to be a whole other presentation as well. But we're going to revisit this little piece over here. And it looks like this under the microscope, and these are beautiful crystals. They are dendritic crystals, and they are in an enclosed volume. And in fact, where the volume ends, the dendritic crystals stop, and they are with a lot of open space between them. And this is very similar to the instantaneous formation of coherent matter-driven crystal formation, instantaneous crystal formation, that is described in the 1992 Solon patent. And this is what it looks like close up, and here's one of these dendritic structures. And of the dendritic structures at sort of 45 degrees from the main structures, there are these growths with hairs, and when we looked at them under the microscope and the SEM, both at Alan Goldwater's Magic Sound Lab and in the Madison, Wisconsin University, we found that at the base we had nickel, and then a little bit higher up we had iron, and then we had a little bit higher up we had chrome, and then a bit beyond that we had titanium, and then we had a carbon kind of a tube coming off in this spike. And so I kind of surmised that this might be because we have got alpha conjugate nuclei production. So if you have a fusion of alpha particles with titanium, that's helium and titanium, that's helium being your alpha particles, you get chromium. If you have fusion of alpha particles with chromium, helium and chromium, you get the iron isotopes. If you have fusion of alpha particles with iron, you get helium, iron goes to nickel here. So this one doesn't happen, it's radioactive. We put that in there in the Parkhomov tables to look at removing radioactivity, which we will talk about in this presentation. Okay, so mugshot in there. So then if you take basically you've got these reactions here, so you can take carbon with titanium and you get nickel, so that's the kind of like directly going to nickel from titanium. And so what I'm saying is, where we see this nickel becoming iron, becoming chromium, and then becoming titanium, and then with a carbon nanotube coming out the end, this to me is basically what's going on is your exotic vacuum object is highly loaded. It's moving around like tufts on a sapphire reactor, so but they are collecting on the sort of ridges. So this is the point of maximum convexity. So they're forming on here, they're self-organizing on there, but then they are moving away, and as they move away, they dump their maximum load. So it's basically titanium plus titanium plus carbon, titanium plus beryllium, titanium plus helium, and then titanium, and then it just has a remaining amount of carbon because it's lost all the titanium, and it then just kind of like, as it's depressurizing or shedding its payload or coming out of coherence. That's how I see that. Now, I've talked about this before, and I'm going to look at the raw data because there's something in there that's I've not been able to share before. But this is the tungsten, the 2% thorium-doped tungsten that was exposed to Ohmasa gas, and you can see that the surface, other than some sort of extrusion sort of marks on it, it's really rather regular. And if we zoom into it, we can see that essentially there's about 4%. Well, let's say that we've got this area here and this area here, so there's a little crack in here. What are we looking at with that crack? Well, it looks like that one here. Yeah, this one is the one that has 1142. Yeah, this is the one that has. Let's get rid of my mugshot. This is the one that has a bit of thorium in it. It's not quite 2%, but it's showing some thorium. And this one up here is showing some slightly higher amount of, no, but about the same amount of carbon, but it's very low, and you can imagine that there's oxides of tungsten on the surface. It is exposed to the air after all, but the vast majority of it by mass concentration is tungsten. Okay, now there is some strontium. So what I'm going to do is I'm going to go and get the raw data for this and share that with you because there's a little bit of strontium. Now this might be what you have with EDS is sometimes there is a X-ray that comes back from your element that has an overlap with another element. I haven't checked it, but maybe the strontium is an overlap and it's actually misreading it as strontium. It might be thorium or tungsten. This is when you need something like wavelength dispersive spectroscopy because that allows you to see with a little bit more definition. Anyway, I think I'll just make sure that is publicly available, that particular thing. Now what I will do is I will spend the time that I would have done if I'd had more time to get this presentation a little bit tighter, putting the slides or the images into the blog after I've published this next week, and that will have the overlays on there and this data too. So let me just find the raw data for this. Talk amongst yourselves. Now, if you want, I am actually considering whether at the end of the presentation to make this presentation actually shorter and to make it more interactive with questions and answers, is to maybe do a Zoom call after I've done the slides here. And if people are interested in that, keep your questions to the end. That would probably be useful. And we can do the questions and answers in a Zoom call if people are interested in doing that. So... Give me a sec. Okay, so I've got a few more data points here. It's not very clear, I'm sorry. Maybe we can get that clearer when I publish it. But we've got a couple of spots here, 1139, 1138, and then we have this area and this area, 1140 and 1141. And you can see that it's seeing something to strontium here, but there's actually no spikes up this right hand side here, and the strontium here is well within the tungsten main sort of X-ray, and so I don't think this strontium is actually in there, although it thinks it is. So in one of the spots, 1138, it's where is it? 1138 here. This one here, it thinks it saw a bit of strontium. It's actually a sizable amount, but if you look at what's happened here is the tungsten on all the other spots is 26.9, when in fact it's 26.9, 26.14, 25.74, but in this one it happens to be 6% is 6.6% strontium and 18.72% is tungsten. So if you add that together, that's 24, 25. It's within the range of these. So I think the strontium is an erroneous signal. That is actually part of the tungsten. So for full disclosure, the strontium is actually a fake signal here. Again, with this one here, 1138, it's saying by atom sent. You can see it really is the missing bit from the tungsten in that sample spot. And the one I've just showed you, I think, is down here. This is the one that I just showed you before. And that's actually the one that was on my ICCF 22 posters. In fact, I'm going to be showing you quite a lot of slides from my ICCF 22 posters. I found them. They're absolutely massive PDFs which you can print. They need to be about 1 and a bit meters wide by 2 and a bit meters high. So you'll be able to print these things if you wish. I'm going to make those public this week. Now that I've found them. So yeah, so that's the data you can see there. So that is the raw data to begin with. So let me go and back to the presentation. So you can go and see this composite video on the YouTube channel. And this is Hoshi I was working with, who actually managed the gas generator. This is Dr. Ohmasa. This is Sho, and this is the scientist that presented at ICCF 19 or 20, where in Japan, and he has this theory about the clusters, the water clusters, and it's a good theory because it does appear to form these structures, these kind of buckyball type structures. Anyway, this is Dr. Georges Egli, and what I have him doing here is in all other experiments for sort of Brown's gas or HHO, oxyhydrogen gas or whatever, the tendency was for researchers to go straight for the most refractory high temperature metals. And it always seemed a little bit suspect to me when I was getting ready for this trip, that it was just like, oh look, it's disintegrating, or it's turning to it's a subliming, or something's going on. It didn't really look like it was going through much phases. It was just going from gas on nothing to smoke. And I thought, well, you know, I haven't seen much analysis of the tungsten in these experiments, or the titanium in these experiments. So I want to be doing that. But also, there's a lot of fumes coming off. I wonder if we can capture those, because if we saw on the tungsten the exact same thing as we captured in filters, then it would be harder to say that the tungsten just got contaminated. So you have the welding rod, the bit that I've just shown you is on that same welding rod where it wasn't exposed to Ohmasa gas after it was exposed to Ohmasa gas. So it's somewhere on the same welding rod. And then the bits that I'm going to show you in a minute are where it was exposed to the Ohmasa gas. And I've actually published some of that before. And then we are going to show what you see here, held by Mr. Egli. This is a vacuum cleaner. We had very little time to come up with an idea, so I thought, have you got a vacuum cleaner? This is actually the filter that everyone's kind of filters people have been wearing these last several years. And the idea was to not get this burnt and allow for some capture of the vapors coming up. And you can see the published video on our YouTube channel. Well, what did we see? Well, this was published at ICCF 22 in the poster presentation, but you can see that what we do see is a lot of carbon, okay? So remember where we were looking at it before? The carbon here is about by mass concentration. So let's just check what it is in the other slide. But in mass concentration, it's 4.54, 4.42. Here we've got, we need to look at the raw data to find out whether this is mass. I suspect it's not. But anyway, I think that this, either way, is very, very high compared to what it was originally. And what you can see is that there is disruption to the surface, and there are these things that have bored their way through in a very similar way to the way you saw those channels on the top of the on the, how should we put this, on the Vega Valley. So you saw those plasmoids, these exotic vacuum objects, these microball lightnings burrowing between the two brass plates and leaving very similar type of tracks to what you're seeing here, with something at the end. Okay, and it's burrowing down here and burrowing down here. And so when I see these kind of things on samples, it's interesting to look at the overall surface here, but it's also interesting to look at spheres and features that appear to be at the end point. So what I've done is I've done that in this area down here. So you can see I've selected this thinking it may be there. This may be something in this little branch here. I've got something maybe here, is probably there, and so on. But what you can see is in every single case there is calcium. There is calcium. Okay, but there are also these other usual suspects. Carbon and oxygen were there to begin with. You've got sodium, magnesium, aluminium. I mean, there's a lot of aluminium there. We got 6.8%, whether it's atoms or mass, it's still relatively significant. Silicon here, 5.9%, 2.7%. Sulfur, this is the sulfur that we saw on the 10 yen coin. And you'll see that Slobodan Stankovic also observed. And we've got potassium here, much lower. I mean, one could question when you are doing samples, when you're getting under 1%, it's sometimes you don't necessarily consider it meaningful. But I have to say, what I did, I let very, very large numbers of samples on Alan Goldwater's SEM to determine these figures that using these maps. I spent very long samples, and so there's a reasonable chance that this is accurate. Here, calcium in every state, 14% here. I mean, that is just huge. So in every single point, it didn't matter where we looked at this surface, all of these points, and to be fair, I did in this particular shot choose features on the surface. That they are all containing calcium. And the interesting thing is, when you type into the MFMP's reaction calculator that was initiated by a gift by Alexander Parkhomov and coded by Philip Power in New Zealand, thank you, Philip. Other than the titanium here at the top, which is with a rare isotope, W80, 180 is actually only 0.14%, so we wouldn't expect to see a lot of that. The next group of isotopes, they fission to calcium and xenon. Calcium and xenon. And if you look at my ICCF poster, what I say in that poster is that I think tungsten is like 10 atomic units size, like an arbitrary figure, let's call it. And calcium's like 25 or huge, and then xenon's absolutely massive. And if you can imagine that an exotic vacuum object is boring down these channels here, and it's consuming tungsten. It's consuming tungsten, probably some oxygen as well. It's half in and half out of the surface. Maybe it's actually under the surface a little bit. And it maybe it's traveling down some of those ridges in the structure of the extruded material. And it consumes this tungsten, and then at some point the coherent matter sheath collapses, and then all of that matter has been reorganized in this intense pressure area. It's an intense pressure area. So what I'm saying is, you get this coherent matter structure form, and it's pulling the material in. It's pulling the material in, and it's stripping the electrons off. So the nuclei are and then being crushed into this very thin membrane, and you get to the point where the coherent matter, for whatever reason, destabilizes and it blows up. And all of that matter that's been reorganized comes back into our free space. Now, it's more efficiently packed as nuclei, But as nuclei, when it's regained its electrons, they are much, much larger. The calcium atoms are much, much larger than the tungsten atoms. And the xenon atoms are even bigger. So maybe when that comes out, it goes poof, and it's like it inflates in free space again, and it smashes that tungsten upwards. And that is this kind of very violent kind of fuming that you get coming off. It's actually literally shredding the material. It's shredding it. So the fact that calcium is everywhere, and it's the most likely product if you've got an intense coherent matter exotic vacuum object structure going through this tungsten, then this was very, very interesting to me. Now, let's look at some other areas here. Again, we've just got a whole range of different sample areas, a large sample area here, points and stuff on this overall structure. And we can see, let's forget this 2.62 strontium. I suspect that should be 11.62% on the tungsten. And that makes sense because there's less of anything else on this line here. But let's have a look at some of these. So this is actually atomic concentration, not mass concentration. So relatively speaking, the mass on the tungsten would be quite high, even when it's only a few percent. But we can see here, what have we got here? Well, firstly, it's calcium. Calcium in every single line. Calcium in every single line. And we've got 6% calcium here. 1146. What's that? 1146. 1146. There we go. 1146. Ooh, can I even see it? Have I got it on the frame? 1146. Can't see it. Well, that's not very good, is it? 1148. 1147. I don't know where that's gone. 1146. Okay, well, I don't want one of those. But anyway, we have a. Is that the whole? No, that's 1154. Let's look at the big area here. 1154. 1154 down here. Well, 1154, which is looking at the whole area over here. This is 50.96 by atomic concentration. So really, a lot of the tungsten, one can imagine, has disappeared from that, if that's actually what's going on. But remember, if we go back to the previous presentation, and I'll pull that up just now, what do we need to bear in mind? Well, firstly, we need to bear in mind that that Yule Brown said that, or was reported as saying, the most startling claim by the inventor in the press is that the gas produced in his process can reduce nuclear and toxic waste to harmless carbon. This is from Imagine magazine in 1988, a year before Pons and Fleischmann announcement. And Takaaki Matsumoto said, very amazingly, it was also found that later that the ring products consisted of conventional elements, mainly carbon. Mainly carbon. That would be like 50% or more, wouldn't it? Not dependent on the collapsed materials. Not dependent on the collapsed materials, i.e. anything you put in, whether it's radioactive or not, will end up as mainly carbon. Okay? So let me go back to the previous presentation. Or the one we're on today, rather. Okay. So we saw a couple of features, and I've discussed these in other presentations. So this is the hexagons that you see, and Matsumoto observed many of these on different systems. We've seen, there's two actually on here. This might be a pentagon structure, but you do see hexagons and pentagons, okay? And this is our, it's actually three structures here, but this is our pretzel here, and we've discussed that in other presentations as well. But I have here a image with the pretzel, and I'm looking at various elements within here, but as you can see, other than 1173, wherever that is, absolutely everyone has calcium again. So it's really showing a very strong pattern for producing calcium. Now, just to let you know, when this was done, in fact, I might even have the plastic. Oh, I have the plastic tubes here. Do I have the plastic tubes? Anyway, there were plastic tubes, and as soon as the experiment was done, they were kind of like put in the plastic tubes. Anyway, so this area here, this sort of smoky area, which you can't see because I'm not showing you, this smoky area here over this circle area, but 50% and going up to the central area here. This is 76.1% atom percent of carbon. It's massive. And this is a film going over the surface. This is exactly what Matsumoto said he saw. He saw regular production of film. And you're going to see it when we look at the indium as well. Okay, so again, we've got aluminium, we've got silicon. There's a little bit of sulfur in this one, not so much. Iron produced. And tin in this case, and that's interesting because if you take tungsten and you take a light element, well, tin's in the center of the periodic table, and tin has the most stable isotopes, which is interesting in its own right. But you can imagine that it's basically averaging into the center. So there we go. We've got some tin production going on. Okay, so what did we see in the filter? Well, here are the carbon filter fibers here in the same kind of filter you would use, like, it's easier to describe these things these days because everyone knows what you're talking about. It's a filter like this. Okay, seen one of those before? All right. So these are the fibers in the filter. And these are some particles that were captured using that vacuum cleaner by Dr. George Eagley, as you see here. And this is the filter in question. And so we captured into that filter these particles. And looking at them, what do we see? Well, we see calcium, calcium, calcium. I've taken a 1230 here is on the fiber here of the face mask, and that reports no calcium. What is 1230 no calcium? 1228 there doesn't appear to be any calcium in that bit as well, but there is strontium and tungsten. In fact, all of them have some tungsten, but the sample point that I have on the actual fiber is reporting basically nearly meaningless amounts of tungsten, whereas the other ones are at 1% or more atomic concentration, so that's quite a lot by mass. But yeah, essentially pretty much everywhere you've got calcium in the particles captured, and you've got these sodium, aluminium, silicon, phosphorus and potassium and iron. All of these things that we saw on the George Ohmasa 1970s type carbon arc in water or air experiments that we talked about in the first part of this presentation. And I have here also some maps of this, which you can see. So again, I've taken the same shot and I've done a map, and you can see the placement. This down here is the carbon area. You can see where the oxygen is mostly on some of the particles that have been captured. The sodium is on two large chunks of particles that have been captured. Don't think there's no chlorine in there. This is good. If there's sodium and no chlorine, that rules out, and in fact there's potassium and no chlorine, that rules out that this is sweat particles or salt to a certain degree that might have been captured from the environment. And you've got aluminium again. These synthesized fragments here that have, I would imagine, blew off the surface have and what do they have? They have sodium, magnesium, aluminium, silicon, phosphorus, not so much sulfur, but that was borne out by the other data. A little bit of potassium. This chunk down here has a lot of calcium, but the other two have a little bit of calcium as well. Very little titanium, and not so much of everything else. and all of the particles captured here. You can see in this map down the bottom right here, every single particle that's been captured in these fibers has the tungsten. So this was a test that essentially, when you look at the form of the test, it took an hour to come up with this concept. So it took longer to argue whether we were going to test the Ohmasa gas than it did to come up with the idea about how to test it and to get all the things to do the testing and do the tests. Apart from the analysis, that took a long time. But so this is actually a metal bucket here. The tungsten rod is suspended in free air in that metal bucket. And you have the vapors going up here, and you can look at the experiment. It is extremely short exposure, really short. And I guess if you were to replicate this and you had an Ohmasa gas device or something that produced gas that was of similar capability, if that's possible, then I would imagine you could conduct this whole test if you had all the pieces together, in maybe 20 minutes, half hour. No more than an hour, and then the analysis would take longer, of course. But the thing was, it was so satisfying to find none of these elements, apart from an extremely small amount of carbon and a small amount of oxygen, of course, on the unexposed rod, and then large numbers of elements that are the type of elements that people have in their body for life. So what I'm saying is, if you went to another planet and it had water and it didn't have enough elements to get going with life, you could use the water with ways that we know to produce HHO gas or Brown's gas or Ohmasa gas, oxyhydrogen gas, and you could then use that gas with the elements to create elements for life. And so this really is about terraforming. Okay, and so it was very satisfying to have that on the sample, but also to have it in the particles captured in the filter. And I think this really is an absolute slam dunk. This is exactly how it works, and it's only people who haven't got the courage to find out that their education has taught them something wrong that would desire not to do this experiment. It's like I'm willing to make sure that I stay ignorant of things that can be tested with a small amount of my time. And the textbooks are absolutely correct, because they're already in a textbook, and that is the law of how science is. If it's in the textbook, then you can't do transmutation, and absolutely Brown's gas, HHO, oxyhydrogen gas, Ohmasa gas cannot do this, because my lecturer told me this cannot be done. Well, I suggest they try and use a little bit of their life to find out whether this is real. If it's not real, it's not real, but I suspect it's real. Okay, so yeah, so that was very, very, very satisfying. Then the other thing was, I chose to do an experiment with something at the opposite end of the scale. So there wasn't enough, in my opinion, looking at what these vapors were and what it was actually doing. Was it really melting the tungsten? Well, we showed on that day it was not reaching anywhere near the temperature required to melt the tungsten, at least on a macro level, observable by a bolometer. But I thought, well, you know, I kind of had a hint, and maybe it was in the back of my mind from Slobodan Stankovic's presentation at ICCF20 in Japan. Maybe that was what was in the back of my mind. The temperature that these type of gases operates at is a lower temperature, and then there's an interaction temperature depending on what's in the gas as an additive and what they are contacting with. But I thought, if it is a very, very high temperature, then I'm going to choose the most laughably extreme thing that couldn't possibly deal with temperatures in the thousands of degrees. And so I chose indium. And the thing about indium is it has an extremely low melting point. It is 156.6 degrees centigrade. And I chose that for the reason that 156.6 is supposedly just above the temperature at which Ohmasa gas, some people reported it was operating at. But other people think, in fact, even Ohmasa was convinced that it was the gas didn't burn your hand, but it must be operating in the thousands and thousands of degrees centigrade. And so I thought, well, if we choose an element that is about as low as you can get a metal without it already being a liquid, or, you know, the gallium's liquid at body temperature, but it's a solid at air temperature. But if we had something that is as low as we can possibly get it, that doesn't ignite in air. So all of the alkaline metals, if you get like the bare alkaline metals and you light them in air, then you can get them to explode. And so that's not going to be a non-starter. So I chose indium for that reason, but I also chose it because 95, 97, a very large proportion of indium is actually a beta isotope. And so if there are exotic vacuum objects involved, maybe they will be interacting with that beta isotope, and that will accelerate their ability to transmute matter. So those are some of the reasons. If you go and look at on quantumheat.org for the Project OMAR and so forth, you look at that, and also for ultra, you can see the reasonings why indium was chosen for these experiments. But let me go back to the presentation now, and I'll show you for the first time the indium experiment up close and personal. And so we'll go there now. And so here it is. And so this is the jet. This is the Ohmasa gas coming out, and the indium is over there. Now this indium is 75 microns thick. 75 microns. It's about as thin as a human hair, right? So I chose it not only for its comically low temperature, but also for its comically thin, structure. It's like nothing there, right? It should fail instantaneously. Well, I'll show you the real-time video first, and then I will show you some slowed down, just a couple of sections in there. And so here's now. Sorry about the low quality here. This is running on a this camera here. This is a GoPro Hero 3 Black 3, yeah, and it has a rather low resolution. The other thing is that there are flickering when you do high frequency frame rates, high frame rates. There's flickering with strip lights, and so unfortunately you'll see this. So if anyone's got epilepsy, I'd suggest you look away now, because there is some flickering in this video, so sorry for that. Okay, so here we go. I thought this would basically disappear instantaneously. I thought the Ohmasa gas would hit it and just disappear.
It's very low melting point. Oh. Try and come up from the bottom and avoid touching this, because we'll set it light again. This bit until about here, but come up from the bottom because it will drip. Okay. Burning.
Okay. I don't know if you saw that, But I've got a couple of little GIF anims or shorter versions that came out of that. But the indium lasted longer than titanium, and it's 75 microns thick and supposedly melts at 156.6 degrees centigrade. 75 microns thick, 156.6 degrees centigrade. And it is seconds and seconds and seconds and seconds with the direct flame on it. And it is glowing incandescently white. It's glowing incandescently white. But it's not dripping. And it's 75 microns thick. What is going on? It's absolutely madness. Madness. I'll show it again. I'll zoom it on a bit to where the flame's coming in.
Burning.
So it appears that it's actually softening the metal, and I'm going to show you in the next slide. I will show you it's slowed down to, I think, maybe 12 or 24 times. I don't know, because it was 240 frames a second. Maybe I slowed it 10 or 20 times. I can't remember actually. But I'll show you that section of it. It's lower quality, so sorry about that. So we've got our melting point here, 156.6 degrees C. And I can see Slobodan Stankovic has just said here that he determined the temperature between 120 and 150 degrees C. And with the Optris PI bolometer that we have, we determined it to be about 131 degrees centigrade, 131.5 or something for Ohmasa gas. Okay, so and I don't know why it's not showing that video. It's not showing that video, so I might have to cut a different video here. I don't know why it's not showing that video, sorry. It obviously doesn't like to show an MP4, so I have that as a GIF anim. So if you just give me a second, I don't know, it's not showing it. So I will show you the GIF anim of that, which I have prepared somewhere else, hopefully. Talk amongst yourselves. What's gone wrong? Okay, I will play these videos directly. Okay, so this is the first of the two videos I wanted to show you. Okay. Did you see what's happening there? Did you see what's happening there? I'll play it again. It's not really melting. It's not really melting. It's turning to jelly. Watch it again. It's like it's gone into a piece of rubber, a rubber sheet. It's not melted. It's turned to jelly. I'll play it again. What is going on there? What is going on? It's either liquid, because it's the thickness of a human hair. It's the thickness of a human hair, and it's meant to melt at 156.6 degrees centigrade. And this flame that's coming down that's meant to be... Look, everyone agrees, I think even Slobodan would agree, that the temperature of the flame is below the melting point of indium. So what is actually going on? It's not melted, but it hasn't not melted. Did I get that right? The right number of knots? It's turned to jelly. It's jellification. Let's watch it again. Look, it sloughs down. It's like hanging like a soggy rag. It's moving around like a piece of jelly. Absolutely crazy. Yes, Corky, this is the Hutchison effect with a gas. It's the Hutchison effect with a gas. Or conversely, that the Hutchison effect is the same as this gas. They are doing the same thing. I believe they are creating coherent matter and exotic vacuum objects, and those are going into the metal, and they are changing the way that the electrons are able to hold the lattice together. This is why, in my view, you can weld all kinds of different metals at different melting points to other different metals and even to ceramics, because you are changing the way the electrons behave, so you can bond things together with these changed electrons. So when I saw this, I could not understand what I was seeing for at least a minute. Because it's turning to jelly. 0.75 of a micron. It's the thickness of a human hair, and it has a temperature that is above even Slobodan Stankovic's elevated estimate for the temperature of oxyhydrogen gas. We measured the Ohmasa gas around about 131, sort of that 135 degrees. No hotter than 135 degrees. So in theory, it shouldn't be melting the indium, but it's not melting it. It's jellifying it once more. Okay, so the next thing I want to show you is a little bit on in that video. Let me go to this one, I think this is one, yeah. So what's happened in this next video is you see it turning to jelly, and he moves the flame off, and then he moves the flame back on, and he initially moves the flame back on to the piece that's hanging down, okay? So yeah, so he's just moved the flame away in the previous video, and you can see he's moving the flame. Here's the flame jet, and he's moving it back, and he hits that bit that's hanging down the furthest, okay? And he then moves away. Now what does it do? It glows yellow-orange. It glows yellow Cheeto orange. Okay? And then he moves away, and it's gone to black. Now, it could be indium nitride. And indium nitride is a semiconductor. Okay? Because there's nitrogen in the air, and I think indium nitride is black. Maybe. It also melts at a much higher temperature. So you can imagine that then this is forming a skin. Let's find out what temperature indium nitride melts at. So indium nitride melts at 1100 degrees C. So it's still well below the melting point or the temperature at which even titanium should fall apart. Because titanium's like 1700 degrees C that it should melt. And we see titanium almost instantaneously, even when it's 1 millimeter or 2 millimeter thick with Ohmasa gas, we see it basically go mad. Now, I do know that in air, titanium, when it gets to like 100 or something, 1,000 degrees or something, it can actually self burn in the air, and that raises its temperature automatically. But I'm being approximate with the data there. But in this case, this temperature is definitely not at the temperature that titanium should melt, and definitely not at the temperature that tungsten should melt. So even if it is forming indium nitride, but then if it is indium nitride, then if this is indium nitride here and it got to the high temperature, I don't know. Anyway, the point being is that why doesn't it fall off? It's just 0.75 of a micron. I'll play it on. Okay, so there's that one, and I'll just play that once more. So again, it comes on, glows orange, yellow, and then he comes away. So we've got a black area here, but notice that all of this area is still here, but it's still flapping around in the breeze. And this is a high-speed jet, and it's flapping around in the breeze like a piece of jelly, rubber. It's holding its form. It's holding its form. Big blob at the end here, 0.75 of a micron, jelly sheet, but it's still not able to break it. Crazy. Okay, next one. Okay, this is not so interesting, but we'll show it anyway. Maybe that will work in the presentation, that one. Sorry for not being perfect today. Why would it? Oh, I know why it's not doing that. Sorry. God. Okay, this is just a GIF animation, so it's going to be rudely bad. So, as I said to you, and when you look at this, and I will do more breakdowns of this, as the jet of Ohmasa gas is hitting the material, at certain points it is shooting out these plumes, and I think even in some cases they come round on themselves, these intense jets, and I believe that's some of the reactions that you're going to see the aftermath of when we show you the analysis data, which I'm going to try and get for you now. Okay, so here we have, and I will show you the whole plane here, but these are a typical structure. So you have the indium oxide on the surface here, indium maybe nitride, we'll have a look at that in a minute. And then you have these areas that are broken through the surface. And here's another one, and another one here. And they also have these little perfect little octahedral structures around here, and I'll explain what those are. Here, and I haven't put the data there, but I will do when you get these slides. This is what I'm talking about with this beautiful carbon film that we saw on the tungsten. But here, it's ejected out of this. It's kind of been blown out and fallen down and become part of this. And we'll look at the other elements that we've got in here. Again, look at this eruption here, this dome. Okay, we're going to have a look at all of these, but I'm going to first show it all in context. So let me get that image up. And this was all shared in my poster at ICCF 22. Okay. Give me a second. Okay. So those 104, okay. Nearly there. Okay. All right. Maybe you can see this. You will want to show you. Okay, so we've got 3 spots here on our indium. We've got the indium basic area here. So this is the exposed 75 micron material, the raw material. And if we look down here, the indium, just this kind of nice smooth area here, 1106. 1106 is 90%, 90.5% is indium by mass, I think it is. And we have 4.1% is carbon, so there is some carbon in there. 0.84% nitrogen, so it does appear to, and oxygen there, so there is some sort of nitride and oxygen on there, and then the rest is pretty clean. In terms of these spots here, these are essentially in addition to the other elements. For some reason it doesn't have any nitrogen, but it has higher concentration of carbon, higher and sodium and chlorine in there. So it looks like a bit of salt on there for some reason. There we go. Might have been my sweaty brow. But there we go. That is the raw material. So let me get you the exposed material. So here is a tile map of this area on the indium, and again this was shared in the ICCF 22 poster session, and you can see these planes and then these what I call volcano peaks going on, okay, complete with these kind of stretch marks as they've been torn up. And if we zoom into this, it's quite nice high resolution. You can see these ejecta from the volcanoes. So firstly, some of the volcanoes have just got their plume here. And this one, I said I'd show you something that looks nearly identical to something from Matsumoto. So let me go and get the thing that I'm referring to over here in the previous presentation. And it's this one down here. So remember I was talking about these ejections from spheres. Okay? And here's a sphere, and here's this ejection here. And he's basically saying this is mostly carbon. And it's a lot more than this sphere in terms of size. But you can imagine if this is a lead sphere and it's got 204, 206, 7 and 8 isotopes in there, and this is carbon with just 12, 13 and 14, most likely 12, all of it, then and possibly silicon in there and so forth, then you can get a lot of carbon 12 for 1, 204, 206, 7 and 8 out of the lead ball. And so this is, to me, absolutely fascinating. And at this point, I think it's fair to show no, carbon from carbon dioxide in the air, no, definitely not. There's a very low proportion of carbon dioxide in the air relative to a very large plume of carbon coming out. So I'm going to show you something from Slobodan's work, and I think that's important to show at this point. So, because it ties into this quite nicely. So thank you to Slobodan Stankovic. Here we see a sphere. And when you look at the elements here, I think we'll find that these are calcium. These structures here that are 50% into the surface. And I believe that's because these are EVOs that came along after this had disrupted and came back into our 3 space and attached themselves to the surface and then disrupted themselves. But they had a different sort of vacuum pressure going on in there. And you can see his ejection here. And when we look at his data, I think we're going to find that this is largely carbon. Okay? It's a slightly different angle on it. And here is something that is in the carbon plume itself, and it's a sphere. And I would describe this as an aggregate of aggregates. So you've got different EVOs that bubbled together into a cluster and then were captured into one big EVO, and then it cracked, so you get to see the inside. Here's another one, similar kind of structure, a bubble of bubbles. Anyway, we're going to come back to Slobodan's work. Let's see if I've got the data here. Yeah, so the data here, if we look at this, is on this ball here. We have, this is spot 1. We have silicon, aluminium, calcium, iron, magnesium, potassium, sodium. These are all the things we saw, remember, coming from our tungsten. But you're going to see these same things appear in our indium. And this is starting from graphite mostly. Okay. Now, to be fair, he saw a high concentration increase. And in certain instances, the increase is so high that the amount of material that's removed, if all of it was that material, it couldn't really reasonably account for the, you know, the percentage of the contaminant. If, well, basically it would be impossible. And Slobodan can talk to this himself. For the amount of material to be in these little structures. Basically, the amount of material that's lost based on the proportion of contamination in there to begin with, if all of that material that was lost was these elements, in these proportions, it would be impossible because there would be too much compared to the contamination in the original carbon that's lost, graphite that's lost. I hope I got that across. Go and look at the question and answers in his ICCF 22 presentation. He actually does that better than I've just done. Okay, so let's come out of there and see if I can go to them. So yeah, so on the surface here, on the surface here you've got these little things, and he looks at one here, and what have we got here? Calcium, it's high. Again, it's carbon and oxygen, so, but yeah, it's more of the same. This is interesting, it's another sphere here, but this one's much more aluminium, and it has this sulfur and chlorine in there, and he didn't have that in the original graphite. One of these little structures, we have lead in there. Lead's commonly produced in Lena. I talked about that in the first part of this presentation. Tellurium. This is interesting because we see tellurium in the center of the coral twist sample from John Hutchison. Okay, so we'll come on to that one in a second. And which one? Oh yeah, so in this case he is showing the plume here. Let's look at the plume. Well, the atomic concentration is 50%, okay, with 19% aluminium. So this bit that's come out of here is a high concentration of aluminium, and you know, this has aluminium in it as well, okay. And we know that what is aluminium? Well, on the George Ohmasa reaction tree, let's go and have a look what that is. The George Ohmasa reaction tree is nitrogen that he had in his air and carbon fuses to make aluminium. So it's not surprising that when he's doing this reaction in air that he is synthesizing aluminium. Okay. So what I've shown you is Ohmasa gas, Matsumoto in the case of Matsumoto, he's using lead, and the lead is doing AC discharges in potassium hydroxide or potassium carbonate. But in potassium hydroxide alone, in light water, pure light water, in a situation where there is no carbon, he is synthesizing abundant carbon. And the phrase he uses, and the phrase that Yul Brown used prior to 1988 when it was published that he was making these claims, it's mostly carbon. And what we've observed with tungsten exposed to Ohmasa gas, indium, as you will see in a minute, exposed to Ohmasa gas, and carbon even. Well, understandably it's carbon, but you're also getting these other elements, but still the plumes are mostly carbon. So let's go back to the presentation. Okay, no, I don't want to do that. I'm going to show more of the merge image here. Okay, so we're going to have a look at some of these plumes, like so this volcano. So sometimes you get an explosion, this raised area here, and this debris field. Okay, sometimes you just get the debris field at the top of the volcano. And the interesting thing is it comes out, and in some cases it comes out and it freezes. It freezes almost instantaneously as it comes out. Why? Why is that doing that? It freezes in like free air, as it were. There's something that's been ejected and snapped off or whatever. This may be contamination, I don't know, but it looks like more of the same. There are also these spherical cavities, and there's one very interesting one down here which has got this 120 degree kind of split plane on it, which we've seen in other Lena systems. But again, here we've got the volcanic plume, here we've got the you can actually see the debris, so it erupted over here, and you've got the eruption sort of cone around here. You've got the eruption cone around here. It's like the prevailing wind was going down here, prevailing wind was going down here. So maybe the indium, this was facing towards ground, and this was up. And so as this erupted out of here, it was hot, so it rose, and so as it deposited down on the surface, it ended up with these plumes in this direction. This one actually goes in another direction, so maybe that's more ejection velocity. But I believe what's going on in here is you are creating, the EVOs are going into the material, they are becoming coherent. Now, how do you get coherence? Well, you need the same thing at the same temperature in phase. And these things seem to get into phase. The electronic structure is built at electronic speeds, according to Ken Shoulders. And if you imagine it's pulling the indium in, if it is condensing that matter, it may be increasing the temperature as it goes down to condense. Like anything condensing has to release that energy, and that energy might be causing the kinetic speed of the ions to increase, such that they collide together and make cold neutrinos. And if there are cold neutrinos in there, and or neutrinos, as Wheeler was talking about, these gluons can be formed of neutrinos as well. If there's neutrinos in there and they're all wrapped up in the coherent matter, they could be interacting with that indium, that isotope of indium, which is the vast majority of indium, that's a beta isotope. Now, it's a very long-lived beta isotope, but if it does interact with it, then it's going to eject a beta particle. And there's something very, very, very special about those beta particles that come out of these cold neutrino-induced beta releases. And I will talk about that in a whole separate presentation. You must watch that. But anyway, the point being is that the structure is eating the material, and then it destabilizes and it erupts. And as we saw in the tungsten, it was able to smash tungsten. Now, if you know anything about micro machining or microelectronics, when you get things smaller and smaller and smaller, they become incredibly strong. You know, incredibly strong. And tungsten's already really, really strong. So to smash that up, it's got to be an immense force, Indium is actually quite soft. And as we've seen, it turns it to jelly. But I imagine it's literally like a magma chamber under a volcano. And then it triggers. And when it triggers, you get an intense flash of heat. And that causes the eruption of actually plasma of indium. That sprays up through the expanding volcanic structure. It comes out of the top. That immediately oxidizes in the air, forming those absolutely beautiful octahedral crystals. And I'm going to show you those now. I've got a close-up on those. They're down here. Look at these. These are stunning. Look at that. Look at that. It's absolute spot-on octahedrons over here. Perfect crystals, variety of sizes in the debris field. Here's a larger look at some of the area here with the various volcanoes and stuff. But these are the beautiful crystals. So they are coming out of the top of the volcano, and then below them erupts the newly synthesized Matsumoto refers to as electronuclear regeneration. Let's say so. He calls it. There's three things. He says. There's several kinds of nuclear reactions which were induced by electromagnetic force called electronuclear reactions, ENRs, were found so far to occur in a special state of hydrogen clusters called itonic clusters, or microball lightning, BL. The nuclear collapse was one of the most remarkable reactions among electronuclear reactions, called electronuclear collapse, ENC. Furthermore, very amazingly, completely broken materials by electronuclear collapse were found to be regenerated again to thin tubes and films of conventional elements such as carbon, oxygen, and iron. The latter process was called electronuclear regeneration. And I believe that is what's going on here. You are getting, in these volcanic plumes that are coming out of the top of these volcanoes, you are getting electronuclear regenerated materials, okay? Not present in the material to begin with. Okay, so I'm just going to show you a bunch of other images in here, maybe. Let me see what I have for you. Okay, I'm gonna look at some of the documents here. Let's see what I got here. Okay. All right, here we go. So, like I say, I'll clean up these. So this is actually the 383 here is the plume that we've just seen, but this is looking at it in a different mode in the SEM, and so it represents it without all this so much spatial detail, but it gives you an idea that this is the indium mostly, and we're looking at 382, so we expect that to be mostly indium, probably some oxygen and nitrogen in there, and these are some of the plumes coming out of the tops of the volcanoes. So let's have a look at what we see there. I don't really know what to expect. So okay, so 381, where is that? 381. Well, I don't even see 381. It's not very useful. But anyway, that one is got some nitrogen in there, so that's good. That does indicate that maybe some indium nitride was forming. 382. What's 382? 382 is the surface of the indium, and that is again okay. So it's still that low concentration of carbon, atomic concentration. And there's quite a lot of oxygen, so it has formed indium oxide on there, and then the majority of it is indium. So that is basically what we would expect for the surface. So we are getting oxides forming and we are getting nitrides forming. But let's look at the 383, 384, 385, 383, 384, 385. So these are ejections from the tops of volcanoes, and what do we get? 383 is 51.63% carbon. Okay, and the indium has dropped from what it was without being oxidized and nitrided to like 40% atomic, all the way to 7.4%. So this is exactly what we see elsewhere. And also we're seeing a bit of silicon here. So this particular structure, 383 here, the one that I showed you earlier, which I'm going to go and find again. Let me find that. Aha. Okay. Not there. Okay. I will do this so we can see both of them at the same time. Let's do that. Okay, I can see both of them at the same time. This is much more useful to you. Are you bored yet? This is about terraforming. It's about making life where there isn't any. So, okay. So, what we are looking at here in this thing over here is this structure up here, which I believe is basically a dead ringer for the one that is in Ohmasa's book, which we showed in the last presentation, and which was nearly at the end of his research, which were these ejected materials. This is like the carbon films like this, which we showed in the previous presentation, and this one here. So that one there. So that there. If I rotate it, I believe that there is something pretty much identical to what we're seeing there. And he says it's mostly carbon. And guess what? It's mostly carbon, 383. Okay. Let's see what else we have. We got some other spots here. These are, okay, so this is, maybe it's on this area, I don't know. Is it on this one? I think this is a different area I zoomed into, but this is in the main presentation, so I think it's this one here. Yeah, if I show you this quick. It's this one here, this structure here, and we'll look at the elements on there. So I'll zoom into that. So the elements on here, we've got a sphere called 392 right in the top of this little volcano, like a. This is 392. What do we have there? 392. Indium's gone down to 9.64 by atomic concentration, but the carbon's over 50%. There we go. And we've got some iron going on there. Hold on, 391. It's 2.37% iron. It's got silicon 2.38%. It's got aluminium in there. All these things that were observed. Chlorine there. Let's go and have a look at that. That's 391. What is that? Where is that? 391. It's right in the center of that volcano. Yeah? Now, what did Matsumoto say? He said you get the nuclear reorganization, it comes out of the white hole, and on the outside you get the light elements, the carbon, the oxygen, and so on, and on the inside you get the iron and so forth forming, and that's what I believe is exactly going on there. What's that? 39? Is that 399? Is it 39 or 309? 309? 399? No, it's not there. Anyway, so you get the idea. We got iron, chlorine, and so forth. What have we got on this one? So this is quite nice. This one that I showed you earlier. We got it here. Yeah, I've got it here. So this is this one. If it'll show me, if I drop this one down and go to here. Sorry. Oh dear. Yeah, this plume up here and these sort of film structures, this bit coming out here, we're going to have a look at this one. And so let's have a look at him, see what we got there. So 397 is that beautiful sort of Attack of the Martians type thing, 397. So 20% indium, right, it's basically carbon, carbon and oxygen. What's this one? 399. Oh, that's 399. And look at 399. It's got iron, silicon, aluminium, so forth. So what else we got here? This plume coming out here, 398. What do we got there? 398. There's a lot of oxygen. Silicon's that's actually mostly indium oxide. Actually, that one. 401. And 400 is mostly the indium, and 401. 401. So yeah, 401's got some silicon going on there, and plenty of carbon. So, okay, so there we go. I think you get the idea. Like I say, there's lots more to share. This is this carbon film here. Let's look at it. 405. I think that's this one here, which I didn't actually put the data in. So this carbon film we see here, which may have come out of here, squirted out and kind of broken off or folded over. Let's have a look at that carbon film. That's 405. 405. There you go. 44.8% carbon, and it's got some nitrogen in there as well. So yeah, I think basically Matsumoto is correct. And what's interesting is that this is showing whether you go from light or heavy elements, and he went to the extreme with lead, you will get the same kind of elements synthesized. And you could argue that in that experiment by Matsumoto, where he's got an electric discharge with AC, so he's going to get HHO forming around the plasma of that discharge, because when he's one way, he's going to be creating H plus, and then the other way is going to get OH minus ion. So he's actually creating HHO local to the lead. Then he's cavitating, and then he's creating a plasma. So he's basically, in that very simple experiment, he's doing all of the above. He's making Brown's gas, making oxyhydrogen gas, making maybe Ohmasa gas, and then he's igniting it and forcing it to attack the lead. And so it's not surprising that he observes the same thing that we observe in the long form testing. So quite possibly you could take metals and do testing using AC pulses and look for the things that come off and find all of the observations that we've observed. And if you think about it also, when oh god, oh dear, I gotta remember his name now. Oh dear, getting tired. When George Ohmasa was doing his carbon arc in air or in water, when he's doing it underwater, like when Bokris and Sundaresan were doing it underwater, when you're sparking and you're coming away, you're basically got AC because it's going up and then it's going down. Okay, and so you're getting both. So, and as they're coming together, it doesn't matter whether one's a cathode or the anode, you're going to get oxyhydrogen form. You've got a spark. So basically, he's making oxyhydrogen gas and he's blowing it up. So it doesn't matter whether you're looking at the work of George Ohmasa here in the 70s and 80s, or you're looking at the work of Ohmasa or Browns or Matsumoto. In every single case, they're doing the same thing. So why would they not observe the same thing? You just got to look at it slightly differently. Okay. Okay, there's much more that I want to show you with the work of Slobodan Stankovic. So let me just get a few more things up for him. I think the most important is the shells, and I'm going to show you this. This is a shell, okay. And you can imagine that there was an exotic vacuum object, coherent matter structure, and the material's coming in and it's transmuted. And then when the music ends, the silicon that or whatever this is comes back into our free space, and it has to get the physical dimension that it should take when it's got its electrons back. And you end up with this, in my view, an extremely glassy structure. This is extremely glassy structure, and we've seen this in various different types of LENR technology. And I believe that this is because the matter is essentially got no temperatures at all. Why do I say that? Because it hasn't got any electrons. It doesn't have any bonds. It doesn't have any means in which to have a temperature. It can't shake that way. It can't shake that way. It can't do any shaking at all. It can't absorb energy, it can't get rid of energy, because it's just like nuclei, like in a coherent matter. And so it has to grab energy from the environment. And so it splat cools. It cools extremely, extremely quickly. And so it forms glassy structures. It is, let's say, silicon dioxide, okay? But it is a glass of silicon dioxide. And the interesting thing is that I believe these structures here, these regular arrays, and what if you look at them, they are six-pointed stars. And moreover, they are six-pointed stars where every other pair is smaller and bigger. So this is a truncated hexagon. Or is it like this? Is it like this? Is it like this? Is it like that? Like a truncated hexagon of a quartz crystal. If you look at it end on, that's not end on, that's end on. That's not end on, that's end on. Or it could be diamond. It could be diamond as well. So is this a diamond sphere and these are diamond substructures on there? Here, on these little areas here? It does appear that we get amorphous diamond forming in LENR. We saw this, it would appear, in the mining diamonds with with the original Lion experiment, the industrial carbon diamonds were eaten away, and sometimes you had a pit, and in the pit there was a spherical diamond. Is this the same thing that we're seeing here? We know it makes carbon. It would appear to make glassy carbon. So something to hold in mind. The other thing that it appears to make is this. And these are absolutely fascinating because not this particular one. It's not the best example. Let me see if I can go up a there. Okay, so here again, it would appear that we have hollow spheres of material. And this is something that I said that other authors have found, like Anatoly Klimov. And also, it's spoken about by Matsumoto. So I'm not surprised if we're finding hollow spheres. Okay? Now, one other thing that Slobodan found were these, and these are pure carbon, and they have diamond-like facets on them. And they also have, if you look, nanolayer structures inside them. Okay? And here's kind of like a close-up. So you can see it's layer upon layer upon layer upon layer. You can see the layers here broken up. And I think I'm right in saying is, well, before we go into that, there are these areas that are eaten out, these round holes that are eaten. And I believe these round holes are on the sum of convexities, or on a convexity. That's where a smaller ball lightning would form later and eat part of the material. We know it eats spheres and round chunks and channels because we see the spheres eaten out of diamond in the Lion experiment, and we see the channels eaten out of the tungsten earlier in this presentation, but also eaten out of the brass in the Vega Valley sample. So I'm going to show you. So it could have started at a point and then eaten out over the surface, and these were just ones that appeared on an edge and so forth. Now, I think I'm right in saying, and we can go to his ICCF presentation. Let me just find that. And sorry if I get this wrong, but you'll have to correct me if I am wrong. Slobodan. I think what you're looking at here is a similar structure that was taken, I think, and I'm going to have a look at his ICCF presentation in a second, from the Chelyabinsk meteorite. And this is fascinating to me because it has these facets, but you can see on the ridges of this facet, a sphere, in my view, an exotic vacuum object has formed. Here's our hexagon that is eaten out of there. And it's eaten in through multiple layers. And you can see here, it's moved around. It's maybe initiated on one convexity, say here, or one convexity, say here. And then it's eaten around, just like the ball lightning eats in the center of the palladium in the Matsumoto experiments. Or just like the ball lightning goes through and eats channels. And so there's a channel here in the Vega Valley, channel here. But this one, there's a convexity here, convexity here, convexity here, convexity here. I believe it probably nucleated on the convexities of convexities and made one, and it grew and it grew and it came round here. But you see, it's all over here. They're eating in. So I think the original structure formed, but just like the snowballs on cobblestones, smaller plasmoids survived after the main structure was formed, and they went and ate and did more transmutation. And maybe this is a transmutation product you see here. But this is in a meteorite. Now, what do you have in a meteorite? You probably have, I don't know, water from the atmosphere, extremely intense ionization. You probably have ion electron pairs. You probably have plasmoid formation, exotic vacuum object, ball lightning, all of the above. Okay, and I guess this is a zoom in on the same structure. So am I getting this right? Am I getting this right? Is Stoyan still there? Here's a close-up, and you can see on this close-up that there are layers. There are layers. And what I believe is going on there is, again, you get this coherent matter structure. The material comes in. It forms this coherent matter of carbon in this case, but it could have been anything that went in. And then that structure destabilizes, and the carbon comes back into our 3 space. Now, just like we saw on our Higgs electrode here from a Vega experiment, imagine this was the carbon sphere, the pure carbon sphere with those convexities and those facets on it that had formed in a previous event. But now it's in our 3 space. But we've got more ball lightning forming, and they're finding their way to the surface. But as we've shown in Vega experiments, if you get a lot of them, then they all join into one coherent layer, okay, that goes over the whole surface. This process repeats. Then you get another one formed, another layer. It destabilizes, and then it goes again. And so I believe that's what's going on with these layers forming, going in and in and in. I don't know whether the contrast is there enough for you to see that that's going in and in and in, but it is. Yeah, and you can see there's clear layers here. There's a layer, and then there's another layer, and there's another layer. And if you looked at that, I would imagine that that would be like a sphere eating out of a diamond. And, you know, an Evo eating a sphere ends up by eating a hexagon in this case when it's eating diamond. Unless it's very aggressive, or maybe these are more aggressive over here, so you get a more rounded edge to it. But I believe that's what's going on, and there is literally nothing, absolutely nothing, that can prevent these exotic vacuum objects. That you know, no, diamond won't do it. Nothing will do it. If they want to eat the matter, they will eat the matter, and they will probably reorganize it as well. Okay, so I have. I'm going to go to his presentation, then I'm going to do the conclusions, and then I've got a really fantastic piece of news. It was just sent to me by Show yesterday. I'm really happy about it. So, okay, so okay. Like I say, I would advise you to go and look at the original speaker, Slobodan, doing his presentation, but I got some comments to make on this as we go through. So the interesting thing about this presentation is that he refers to George Joshua here, and we got John Bockris, and we've talked about John Bockris and these two fellas as well. I think they're worth having a look into, and in fact I haven't looked into them, so maybe there's lots to be learned there. This is his equipment, this is his lab, this is his jet, and when he does the jet and he looks at it with a spectrometer, he observes the lines of, I think, OH and something else. I think I can tell you. No, I can't tell you there. But what you're not seeing is, well, you're basically seeing OH lines. And what else are we seeing, Slobodan? You there? Okay, I'm going to look somewhere else. Okay, you're seeing this. You're seeing OH down here, and you're seeing OH, and then you're seeing NH. So those are the lines that you see when you look at the gas. Now, the interesting thing is you observe in the cosmos, OH self-mazes. And by saying it self-mazes, it means it coheres. Because if you have a maser, a microwave laser, that involves coherence, and so OH self-coheres. Okay. So that's the flame. This is the OH and the NH, and this is the kind of broadband spectrum that you get when you're exposing to carbon. Now, why are we not getting all the elements that are being synthesized? I believe what's going on here is you're creating the coherent matter, and as the transmutation occurs and as anything gets excited, if photons go out, well, they hit the coherent matter layer, and so they get converted into a broadband spectrum. So I actually think you've got an example here in this spectrum data of this kind of force shield effect that you get with LENR systems that prevents you from seeing photonic ionizing radiation. So he's looking at his different samples here. He's talking about Kevran here. Here's your transparent things and your spheres. Here's the carbon material coming out. And you can see here, actually, on here, that this has a hole in it. You see it's got a hole? Just like we saw on Ohmasa gas, on Matsumoto's work. So I imagine this hole would be burping out a load of carbon, like this one appears to be doing here. It's showing the analysis there, and he's talking about the number of times, the amount of times the original concentration here. So this, I think, was done by chromatographic technique. Here he's talking about the fact that sulfur is synthesized and chlorine is synthesized, which is not in the original analysis, and we've already explained sulfur, and we've observed that in various systems, and I've talked that through today. And so we've observed it on snowballs on cobblestones, on the 10 yen coin exposed to Ohmasa gas. We've observed it in the tungsten exposed to Ohmasa gas, and so forth. So this is another kind of composite that he found. So you can see his discussion on there. So here is talking about these diamond-like structures. So there's one here I was missing to show you earlier. You can see in this case, again, you have the facet-like structures. You have what I believe, like on the snowballs and cobblestones, these are smaller EVOs that after this one was formed came and found themselves on here. They actually might be leftovers of the overall coherent matter structure that formed this, that then just kind of like when we are in the Vega experiments and you turn down the energy, it goes from being all the way around it to being what the Japanese called in 2001 balls of fire that are half on the surface and half in the surface, it would seem. And what you're seeing is here, in my view, is that they like to be eating the bit inside the surface, and in these cases they're forming channels and going around, just like you see on the Vega Valley, just like these channels here. It's all the same thing, like those channels that you can see in there. And again, you've got the layers going on in here, so this wasn't a one-hit wonder. So yeah, I think I might be right. Yeah, so this is I think this is his example, and this is from the Chelyabinsk meteorite. So maybe the other one was or wasn't from the Chelyabinsk meteorite. Now I actually have something interesting. If I can dig it up right now, it would be really fascinating. It's also from the Chelyabinsk meteorite, but it's from a presentation that was given by a Russian physicist this Wednesday. So let me see if I can dig that up, because I think it is quite relevant now. If I can find it, it would be fantastic. Okay. It's a bit data heavy today, I'm sorry, but what I'm showing you is pretty darn special in my view. Okay, so it is. Oh yes, here we go. So this, I think, is also from the Chelyabinsk meteorite. So this is our chap. I can't remember his name, I'm sorry to him. But you can go and look on. It was published earlier this week. And this is supposedly our meteorite. And you can see you have negative ions coming around the outside and positive ions from behind. And then you have this material coming back in from the backside. So this almost looks like you know, a stealth bomber in terms of its electrical configuration. But the important thing is that you have charge separation, and charge separation leads to the formation of exotic vacuum objects. And if that's the case, then it's absolutely no surprise whatsoever that if you've got exotic vacuum objects on your Chelyabinsk meteorite coming in, that you see exactly the same thing in the Chelyabinsk meteorites material as you observe in carbon exposed to oxyhydrogen gas. So, and this looks like a lot of what we've seen in our experiments. This tail shows you that this is a lot smaller. You know, but the thing is extremely bright, and that's just what you see with EVOs. So this is absolutely fantastic. And I just when I saw that earlier this week, it was like, oh, gotta show them that. Okay, so that's your Chelyabinsk meteorite, and this is from Slobodan Stankovic's work. Now, the other thing I asked you to look at was this, which is where he's putting it through, I think, a graphite block or something. If I can show you without it going away too much. Oh dear. Yeah. And it's producing this structure here, okay, which looks like it's twisting. Okay, this looks like the structures that we saw in the Vega experiments, and it's very, very interesting because after Slobodan gave his presentation, there is a question, and bearing in mind this is at the end of it's September 2019. There's a question near the end of the question and answer sessions of Slobodan, and it's by one of the heads of the Russian presentation sessions, who is also a senior scientist at the All Russia Plasma Physics Joint Plasma Physics Laboratory. And that is Anatoly Klimov, who worked with Ken Shoulders. And he asked, having seen this image, he asked what kind of microwaves was he using, and you know, how did you ignite the plasma or something like that. And I didn't quite understand what he was referring to until I clocked that he gave a presentation in the middle of last year, in June, I think it was, of last year, where he talked about plasmatrons, where they had a microwave chamber. They were using microwaves, and then they were discharging a spark, which would produce an ejection through a small polymer capillary. And this was a replication of work that Ken Shoulders had done in the 1980s, and where he found positive, neutral, and negative exotic vacuum objects. But the important thing is here that Anatoly Klimov was talking about microwaves. And it's only when you see what he showed in June last year, you realize that the maser concept, the microwave laser, is, I believe, what is going on here in Slobodan's work. And in fact, I said it at the time. When he first showed me that image, it was at breakfast, I think the day before he gave his presentation. And I said, wow, that looks like it must be amazing or something. And that is exactly what we see going on in the Vega experiments. Sorry, it's not working very well here, my demonstration, as usual. And so let's just have a quick look at what I'm talking about with regard to Anatoly Klimov. And I actually put the links to the slides for this on the blog for this at remoteview.icu. I can find it. So I'm talking about this incredible plasmatron phenomena, and so I'm going to download it right here and we'll see what it is. And so he was, this is a Mach 2 jet of air, Mach 2. And you can see here these same kind of spiral forms coming out that we observed in our Vega experiments by Henk and by Dave. And you can see a larger spiral coming in here and colliding. More spirals. And so you can see spirals here with ball lightning, and here with the Australian ball lightning that I found here. And you can go and have a look at this in your own time, but this is what was discussed by Ken Shoulders. This is one of the things is not mentioned here. In the photo, the camera is looking at the end of a small capillary tube that had an electrical discharge emanating from it, producing the image. And so he says, he goes on about the fact that there's positive EV structures, neutral EV structures, and so forth. But you can go and read that in your own time, and I talk about it in that presentation. But my point being is that Anatoly Klimov asked that question in 2019 and gave this presentation on 17th of June 2020. So he, in my view, released this research from the Joint Plasma Physics Laboratory of all Russia, having seen what was presented by Slobodan Stankovic here. I believe that we are seeing something that is the same phenomena. And the reason he asked what microwaves are you using in here is because he thought you need to microwave excite the material to get these kind of effects going on. I don't believe that. I think you are self-mazing. And what is a laser? It's coherent light. What is a microwave laser? Well, that would be a maser. And what is a baser? A baser is a boson coherent matter beam, coherent matter wave beam. This could well be a coherent matter wave beam. And if so, that would explain how the 10 yen coin got immediately cut out. And it's OH minus that is causing this amazing basing process. And you know, I think John's going to get quite excited when I just say that, if he gets to this point in the presentation without falling asleep, because I think we're seeing basers here, and I think that is what HHO is doing. It's forming coherent matter beams and of matter, bosonic matter, and that's why you get these extraordinary effects, absolutely extraordinary effects. and that lead oscillating discharge of Matsumoto in water with potassium hydroxide producing lead spheres that are ejecting carbon, that is because it's creating coherent matter, because it's using the OH minus self-mazing process. And I mean, there we go. So I'm going to start wrapping up the presentation now. So give me a second. There's a lot more in the slides that I've shared and referred to that I could have talked about, and probably I'll come to talk about those in another presentation. But I just want to close out here. So my conclusion is that Ohmasa vibrator appears to be able to bring about transmutation to both fluids and metals in its own environment, potentially providing a much needed solution to radioactively contaminated areas in the world. Ohmasa gas applied to metals appears to act as an instant Lena, causing large-scale transmutation of elements. Since Ohmasa gas appears to fission heavy elements, it should be suitable for treating dangerous products of the fission industry. It may be possible to test these findings in other ways, and I believe I've shown those ways, some of those ways. So please consider supporting this work. That would be very much appreciated. And critically analyze observations. That's one of the best ways you can support this work, is to listen to what I've said if you can. Listen to what other authors have said, like Slobodan, like Anatoly Klimov, and try and tear it apart with reasoned arguments and references. Donate to support open research. Do research and share results openly and quickly. I think what I've shown you tonight is that Matsumoto's very simple experiments are doing exactly the same thing, but in miniature. You are creating your oxyhydrogen gas, you are igniting it, and you're doing your transmutation all in one little, in one case, I think it was an 800 microsecond pulse. So like 0.8 of a second, that's the length of the experiment. The rest is hard work doing the analysis. Okay, so and so there's some donation links. So then I just want to talk about this. This is the actual slide 55 from O'Day, and this is the scarab beetle. So I think Alan was right about the concepts of the scarab beetle here. Egyptians saw the young beetles emerging from their spherical dung balls as symbols of the sun. Black sun? I don't know, but this structure here, this sphere recessed, is what you would have to do if you were carving it. But it's also what we saw on the top of the Bullburn sample from John Hutchison. It's also what we see in many different things. It's this eaten into the surface sphere of new material. Okay, so the scarab beetle, you could basically liken, they kind of believe it's like for creation, regeneration, transformation, and renewal. I would call those things, the creation would be nuclear synthesis, regeneration would be repair and stabilize. That's like taking radioactive material from fission and repairing, stabilizing it. I think life actually uses potassium-40's energy and possibly carbon-14, because we've evolved with that. But we didn't really get on very well with fission products. And so it's not that you necessarily want no radioactive elements, but I don't think we want the radioactive elements that come from fission products. And so repair and stabilize, I believe, is something that can be done. Transformation is reorganization. This is what you might call alchemy. This is actually making elements from other elements. And renewal is reset. And so when you look at those terms, and bearing in mind, I produced this slide in 2018 in the spring, in January. I received this book in January this year, 2021, 3 years later. That's right, isn't it? 18, 19, 20, 20. Yeah, 3 years later. And I'll read it to you again. recently, the author discovered a nuclear collapse which was induced by the electromagnetic force in the laboratory, because he says that the electromagnetic force, which it is 40 orders of magnitude stronger than the gravitational force, and you can manipulate it in the laboratory. He says, during studying the mechanisms of so-called cold fusion phenomena, several kinds of nuclear reaction were directly induced by electromagnetic force called electronuclear reaction. They were found so far to occur in a special state of hydrogen clusters called itonic clusters or microball lightning. The nuclear collapse was one of the most remarkable reactions among ENRs, called electronuclear collapse, ENC. Furthermore, very amazingly, completely broken materials by electronuclear collapse were found to be regenerated again to thin tubes and films of conventional elements such as carbon, oxygen and iron. The latter process was called electronuclear regeneration. So I believe that all the evidence is pointing to is that the Egyptians knew how to do this. They knew how to do it. Create elements, regenerate, change the elements, and completely renew. And you could say that renew could be converting the energy back to light. This here is a sphere with the wings that we've seen, and this is on a Hutchison effect sample. And I talked a little bit about Grebennikov at the start of the presentation. Okay, so maybe that's where I want to leave it for today with the presentations. I will see if you've got any questions. Does anyone want to? Does anyone want to go to a live chat on a different platform, or is this good enough? We can work this. Work here. I'm a bit tired, so you have to forgive me. There'll be a lot more data and stuff to share. I might split out certain aspects of this presentation and do a better job of it. Okay. So Slobodan, thank you, Bob, for presenting my work. Really, oh God, Slobodan, I've absolutely mullered your work. I recommend people go and see his presentation, but I would see his presentation and listen to what was said by Anatoly Klimov in the questions. And he says, you know, what microwaves are you using? And he says, oh, I'm not using any microwaves. And I now know what was going on in Anatoly. I've not even spoken to Anatoly about it, but I know what's going on in his head. Because he's looking at Slobodan's work and he's seeing these spheres that are hollow while he's observed the production of those. He's seeing this spiral in the center of this oxyhydrogen gas. Well, he's observed those, but he had to go to extreme lengths of complexity to create it. I mean, what you did, Slobodan, is nearly as simple as can get, but you've got to give Matsumoto credit. Without realizing it, he has done exactly the same thing, and it's much, much, much more simple. It's not quite to the level of a 5-year-old can do it with no risk ultra experiment, but it's pretty close. Certainly, I would think that. Well, I think 5-year-olds could do it, but I wouldn't want to let them near 120 volts because that's just not good. But potassium hydroxide is caustic as well, so I wouldn't want to do that. But I would imagine that the Matsumoto experiments, and hopefully we will get the answer back from him. Don't let me forget, I've got a really amazing announcement to say at the end of this presentation. It's absolutely... It's a dream come true, but it's not a dream fulfilled. Let's hold that thought. Put a pin in it. This experiment could easily be done by secondary school pupils, and for very, very little money. Obviously, you would need access to a scanning electron microscope to be able to get the full benefit of it. But maybe some better schools can gain access to that. No, I've not said the good news yet. Okay, so do people want to go? Oh, I see someone. I can see someone's got a question here. So infidel apostle, I just want a Grebennikov box. I think when I did a lot of work on that. I did. It was amazing what happened. It was quite fortuitous, and so that will be a whole other presentation on it. And I want to do some other microscopy and stuff. But I think it's going to be. I've got some interesting ideas and experiments that I'd like to do, but I haven't even done the experiments I already want to do. So. So you are saying we can control temperature with sound. I'm saying that you can, if you can use sound, but okay, sound can create coherent matter. Coherent matter can influence temperature. Both up and down, but it's more like a heat pump. I've got a series on my blog which I've got 2 more episodes to write, and it is what goes up must come down, and I will get round to doing it, but it will be open and shut case, and it basically does use an inherent property of EVOs to do this, and it's pretty amazing, but it's not a case of I wave a hand and you accept it. I have to go through each step, and it's quite a journey to understand how it works. But it'll all be laid out. But yes, you can use this to manage heat. Of course, in the process, you have to transmute matter, or at least cohere it. I mean, it's not trivial. I think one of the things that I've realised over the last few years is that it's mental barriers and educationally driven mental barriers that are holding back so much, and there's really no reason for there not to be abundant cheap electricity in this planet, because nuclear works. We know how it works, and with this technology, the problems of nuclear, which manifest themselves sometimes if certain things are not done correctly, or if you have to deliver massive reactors, this technology can fix those, and so you can have a scenario where you can have small modular reactors, and the uranium is quite abundant in the Earth's crust, and thorium is much more abundant, and so there are options for doing nuclear reaction, and then to take the waste product and rapidly, using simple technology, make it, in my view, safe, and so there should be none of this energy problems, and no excuse for nonsense with climate change, because it's deliberately avoiding the solution in order to tax people for a bad solution, that's one thing. The other thing is abundance of elements. There's no reason why, with proper study, one couldn't find the recipes to create particular elements. And it's like I showed you, if you have tungsten and you have a Ohmasa gas, you can end up with getting elements in the middle, but if you have not so heavy elements or not so lighter elements, your averaging will be in a different place. So you can look to target elements, it will tend to produce stable elements. The way you create unstable elements is to do what Adamenko did, or what Leclerc did, which I talked about in the previous part of this presentation series, where you just drive it to the nth degree and it actually creates super heavy elements that then fission, and then you create radioactive elements and also other elements. Actually, on that point, I will show you something that I put into the in my presentations at ICCF 22. I did talk about tests that I've done with Synthestech in Sochi on one of the aluminium samples from, or one of the samples from John Hutchison. And I reported on my poster session that there was a very large increase, relative ratio of nickel 61, and that there was a very large, I think it was nowhere near as large as the 61 increase, but of lead 207. And so 61 is the only fermionic isotope of nickel, and lead 207 is the only fermionic isotope of lead. And so this fed into my understanding that basically Piantelli, and long before him without really realizing it, because there was no understanding of deuterium and tritium when he observed this, but Langmuir, when he was doing tungsten filament light bulbs, ended up creating 7,000 times the volume of gas, and there was an assumption that maybe this could be atomic hydrogen being produced, and where was it coming from? And I believe it was coming from coherent matter and causing the decay of the tungsten filaments and producing gases, but which we've already shown that it probably is producing xenon, but there would be some excess hydrogen being produced. But certainly Piantelli made his whole patent around the basis that excess hydrogen, or hydrogen in the form of atomic protons, the nucleus of protium, is being ejected, and that those go into secondary materials like boron 11 to go to carbon 12, or lithium 7 to go to beryllium 8, which decays to 2,4 helium and gives you a neutronic fusion. And so the reason I believe that the proton comes out is because it's fermionic and can't stay in the bosonic cluster. It's kind of like more matter comes in and there's a leftover proton and it gets spat out. Okay, and so you get the spat out. In the case of what Tom Claytor did, he used a corona discharge, and the corona discharge, with that, he proved that you can produce tritium. Now, the Carrere brothers, and I think Lord Rayleigh before him used, I think Lord Rayleigh, I think it was in 1936, showed excess energy produced from corona discharges in gases, and one of those gases, I believe, was hydrogen. And so this is not new, but the proof of tritium being formed by corona discharge was awarded to, by this community, the condensed matter nuclear sciences community, to Tom Claytor, formerly of Los Alamos National Laboratory. And I believe tritium gets formed, which is one of the I think it's basically the only radioactive isotope that gets synthesized by LENR if you don't push it really hard, like I was describing earlier, because proton comes out, is stable, deuteron comes out, well, it actually stays in because it's a bosonic. If a triton is formed, like a proton, it gets kicked out, or if it's a balancing triton, it gets kicked out. If a helium nucleus forms, well, that is an alpha particle, and that goes into the bosonic cluster. So everything above that doesn't get kicked out unless it's a boson, but a boson that's stable. And so this is why you get 61, in my view, being increased. I think it was 3.7 times natural ratio in the Hutchison sample we looked at, and that's very big. It was 0.7 times larger, so 70% larger, I think, in the lead 207. And so I was not surprised when, under corona discharge, the work of Irina Savatamova was previewed on this week's Russian meeting, and this will be shown at her ICCF 23 in Jiamen, I think it is, in China, next a week, just over a week from today. And I'm just going to show you that now. So this is me talking about this, and in this video you'll see me talking about the proton, the triton, and so forth. But bearing in mind, if you have tritons, they are very advantageous as a nuclear partner to other elements for transmutation, because they've got these extra neutrons. They really want to become something else, in my view, and the data points to that. So you can use it, and we're going to get to the point of the really exciting news that's coming at the end of this presentation, which I will say after I've gone through this. So on Wednesday the 26th of May 2021, this week, Irina Savatamova previewed her ICCF 23 conference presentation, where she used a corona discharge similar to that used by Tom Claytor, formerly of Los Alamos National Laboratory, to produce tritium in his case. So here we go. You've got this corona discharge, and helpfully she's done the slides in both languages. You have this is the unstable mode, which you don't want, where you have these discharges between the electrodes, and you have these spots, the cathode spots or whatever. So you don't want that. You want it in this corona mode. Now I'm telling you now that corona discharges, you've got this state where the matter is reaching equilibrium. Well, if you've got the same thing at the same temperature and you get it into phase, what are you going to get? You're going to get coherent matter. So that's what she's creating. That's what she's creating here. She's going to be creating coherent matter, and that's what's doing the work. Okay, so I wasn't blown away. It was just like, oh, there you go. As I had observed in Hutchison sample and discussed in my ICCF 22 poster presentations, she also found that she produced an increase in the relative ratio of 61 nickel over natural nickel isotope ratios. So the percent of in the original sample, 63.1 to 65.96. Well, since the natural ratio should be 68, this is not significant. 26 in natural ratio, 29 observed, and went down to 27, but it's in between the two, so that's not significant. 0.93 approximately of 64 and goes to 0.93, that's not significant. But look, nickel 62 was down significantly, and this nickel 61 went up from 1.06 to 1.30. And so of the ratios that she assesses by a different method, it's by far the biggest change. So the multiplicity, so this was making more nickel, and in fact what happened was the copper was disappearing from the contamination in the electrode, and more nickel was being made. Now we observed copper disappearing in the 10 yen coin, and you might see something similar when we look at the Vega Valley. So here we go, and then and for decades, this is synthesizing nickel, and more of the nickel is 61. And in this case, for decayed lead isotopes, she saw a relative increase in 207. So this is a bit like Ohmasa. It's decaying the material. But look, this goes down to, well, basically you can't look at this because there's a mercury isotope, but also it's not meaningful. So where it's reporting 6.29% here, it's not meaningful. So we just look at these ones, and the 208 goes to less than 0.55 of its original ratio. Here it's 0.57, but it's 0.6, so the 207 relatively goes up. So this is essentially the same observation. And what I'm telling you that this means is that the Hutchison effect is doing the same thing. It's creating coherent matter, and it's transmuting, and the observations of a corona discharge system produces exactly the same thing as the Hutchison effect, right the way down to production of anomalous fermionic isotopes. Okay. I'm going to show you this news because it's absolutely wonderful. It's wonderful. It's kind of like it is the yin and the yang after last week's really tragic news, and it came from the same source, Show. And I want the community to see if we can come together and make this happen, because I think it's going to be very special if we can do that. Give me a second. It's worth waiting for. Well, I think so. It's a bad translation. I'm going to try and get a better translation done. But, oh, it's just lovely. You couldn't have imagined this. You couldn't have imagined it. Request for proposal, 9 sigma. To separate tritium from the water which was cleaned tritium with multinuclide removal equipment, such as technology. First proposal submission deadline 2021, September the 30th. This is the guide to contact. Opportunity for the proposer, joint development and the technology licensing, recruitment period, blah, blah, blah. Okay, so we have till the 1st of the September the 30th to prove that we can transmute the material and then propose a budget for dealing with the 1.2 million tons plus of tritium-laced water in the Fukushima Daiichi storage tanks. 9 Sigma is TEPCO Holdings Co. Limited, Tokyo Electric, occurring on Fukushima first nuclear power plants, multi-nuclear removal facilities, blah, blah, blah. Here and after Alps processing water. Tritium from a practical technique for separating, and I'm looking for it, regarding this open call for participants in order to ensure transparency due to its high degree of publicity. If consent is given, the name of the proposer's organisation and name may be disclosed or disclosed to a third party regardless of whether or not proposal is accepted. The results of acceptance or rejection. Anyway, essentially, what they are asking for is for people who think that they have a technique for dealing with the Fukushima nuclear wastewater to come along and make a proposal. I want to make this happen. I believe that we have the technology. I believe that we have the people that's had the experience. Ohmasa is up for it. We're asking Matsumoto to be a consultant. I would like for his nuclear expertise in radiation monitoring. For Alexander Parkhomov to be involved, and for potentially that would be. I believe that if we want to fix the other waste, we could have a twofer where you actually electrolyze and produce HHO gas, but it would be THDO gas. And I think even just burning that gas on a conductive surface may remove the radiation. But it would be great if we could use the what we've learned about Brown's gas, and even hopefully we're doing testing of Brown's gas to actually remove the more solid nuclear waste and deal with that, where you actually deal with both at the same time. The other option is to create the vibration system, amp that up maybe with electrolysis at the same time, or just vibration, maybe looking at different frequencies and so forth, and different additives. I've got a lot of ideas for the right types of salts to put into the water to yield the most effective, stable outcomes from this. And I believe that we have a real shot of stopping the Pacific from having all of that material being dumped into it. And that would be the biggest honour of my life, to be able to do that. And after what happened last week, the learning about that death, it would be just absolute pure magic if we could come together as a community and fix Fukushima. That would really, it would be like, it would be the thing that I would love to do more than anything else right now. So it's really, really just amazing how the world works. So we basically have a number of months window. I know, Slobodan, I spoke to you earlier in the week, and you have a window in I think it is June into July, I think I'm right in saying, where you can join me on Brown's gas testing. If we can verify Brown's gas does a similar thing to Ohmasa gas, then we might be able to simplify or improve what's going on with the Ohmasa gas. But whatever, I think the vibration, we already understand from how the resonant modes can form far from equilibrium systems and micro vortices, and the micro vortices lead to coherence, and the coherence leads to transmutation. And if you've got tritium in there, I believe the transmutation will be faster. And in fact, Ohmasa has already claimed to have observed faster transmutation when tritium water is being used, and he's already demonstrated the remediation of tritium water from Fukushima in 2012. So we have a reasonably proven track record, but I think since going to Japan, we have literally a full spectrum explanation for how it's actually physically happening, and with science to back it up, and patents from military organizations to back it up, and everything's coherent, and so forth. So I believe we can make a very, very strong argument that we will be able to do it. And I would like to be in a position where we can actually have tested by that September the 30th deadline. That would be my wish. But oh my God, with this nonsense cold that's going around, that no one can go in and out of Japan. I don't know what the situation is with America, but I'm already realizing how difficult it is to go to the UK. So there are massive hurdles to overcome, but we've got to give this a shot. I'd rather fail and have given it a try, because the importance of avoiding that radiation going into the Pacific is beyond anything I can imagine right now. And that would be the first step. The second step would be to bring all the evidence together, Slobodan, myself, Ohmasa, Matsumoto, and so forth, to show that we can remediate the solid waste and not leave this thing for generations to come, and use the same techniques to develop technologies to deal with Dendritic atoll and to deal with Chernobyl, whose shell is meant to last for 100 years and has got to be replaced every 100 years, but it looks like it's leaking or failing anyway. So I think we need to have more practical solutions, and the bonus of doing this is that it will absolutely categorically prove for once that Yul Brown was correct, that Ohmasa's observations were correct, that our observations were correct, that John Hutchison's observations were correct, and that everything is this coherent matter, exotic vacuum object type structures going on. And I would then like to involve John Hutchison to clean up the more broad environment by stimulating the production. But obviously we would need to do tests with that as well. And so I believe we're in a position to full spectrum fix Fukushima. And so this was just to have an opportunity to at least put a proposal out there, and I think we've got to work so hard to get the argument and the data absolutely watertight and repeatable. But I think we're nearly there. So let's do it. That was really exciting for me. I don't know what it means for you. Okay, so if you've got any last questions, otherwise I'm going to call it a night. Yes, Slobodan, it's fantastic news, and I really hope we can go and do the tests that are necessary. So we have that window, so let's see what's possible. Yeah, I mean, when I started seeing the observations from my testing of Ohmasa gas in 2019, when I sat, maybe people appreciate. You can listen to Alan on the second video I've got on the blog, and he says every third day I asked Bob to go to bed so I could fix the SEM or something like that, which is basically what happened. I SEM till I dropped, but it was. When I was looking at those volcanoes coming out and the way the plasmoids, the exotic vacuum objects, the microball lightning, the itonic clusters had eaten through that tungsten, and knowing how quick those experiments were, and putting that in context with the claims by Yul Brown, and I just thought, my God, this is instantaneous. Every day of the week, low energy nuclear reactions. This is transmutation at the flick of a switch. It's just unbelievably amazing. And I just thought, when I start talking about this to people and they actually understand it and they get that it's real, it's gonna melt their brains. It's gonna melt their brains, because he was showing remediation of nuclear waste in 1992, and we are here 10, 20, nearly 30 years later. It's insanity. It's insanity, and it's enough to make anyone get really angry that it wasn't taken seriously. But to be fair, he argued that it was making carbon, but I've not seen the data. I've not seen the data, but now you've seen the data. You've seen it from multiple sources, multiple independent sources. I didn't know when I wrote that slide with the beetle on it that's what it was. I mean, let's go and have a look what that character means in what Kepri means. Let's go and have a look here. I mean, if the Egyptians didn't know what Kepri meant, I mean, I just beggars belief, really, that they had to have had this technology. They had to. This doesn't make any sense anyway. You can't sculpt such accurate depictions of how a technology works without actually understanding it implicitly. Kepri, rising sun. This article is about the Egyptian god for the type of robot. See, Kepri mobile robot. It's not that one. Kepri, Egyptian, I get my mouse working, is a scarab-faced god in ancient Egyptian religion who represents the rising or morning sun. By extension, he can also represent creation and the renewal of life. Creation and the renewal of life. This is exactly what it does. Meaning to develop, come into being, or create. The god was connected and often depicted as a scarab beetle. Young dung beetles, having been laid as eggs in the dung ball, emerged from it fully formed, and thus were considered to have been created from nothingness. Yes, this can create from nothingness. But as I showed you in the first slide, it's not quite that. The Egyptians knew more than this Wikipedia article is. Well, that wouldn't surprise you, but anyway, then this Wikipedia article is letting on. Because here, in this slide, you are seeing that they have Ka. This is the spirit energy, and we will deal with what that is in future presentations. We will deal what that is, and it can only be that in my view, but I may be wrong. But the spirit energy, through this technology, leads you to probably what you might call the black sun, or something equivalent to the sun. I believe it is the way the sun works, and this allows you to make matter from nothing. But it isn't nothing. It isn't nothing. It's the spirit energy. You are you're making apparent things. You're literally invoking things, but you're not. You're actually making it from energy. you're condensing the energy through exotic vacuum object production, coherent matter, to create the matter. The god was connected to and often depicted as a scarab beetle. The young beetles, having laid their eggs within the dung ball, emerged from it fully formed and thus were considered to have been created from nothingness. Egyptians believed that each day the sun was also reborn, created from nothing. In the same, I mean, these are just assumptions, really, in my view. The Egyptians knew way more, really. They can't have not done, given what they've sculpted. In the same way that the beetle pushes large balls of dung along the ground, Khepri moved the newly born sun across the sky. Khepri was a solar deity and thus connected to the rising sun and the mythical creation of the world. Yes, I don't think it's the mythical creation of the world. It's the technology that created the sun. Is how the sun works, and it is what created the earth as well, and all of the elements in it. The god and the scarab beetle represent creation and rebirth. Yes, Gordon. Yes, you're right. The clutch is in his hand. The clutch is in his hand. Of course. Of course it is. And I believe this symbol, I might be wrong, but I think this symbol means electric or something. I might be wrong, but I don't know. I've got something in the back of my head that says that this means electric, but you can go and have a look at that in your own time. WP for truth. The Ankh is a tuning fork. Okay, so what do you need to do to make coherent matter? You need to get it in the same phase and the same frequency. Doesn't that sound like tuning? Hey Bob, where do you find your sketch? I'm not sure what you mean. WP for truth. Yes, it sound light and vibrational tuning, but all of them are vibration. they're all the same, really. They're all the same thing. Oh, question link to the okay. I will send the RFP. I will send the Japanese and the So there are some people that might be able to do better translation, so that would be helpful. So tomorrow I will give a link to the PDF of the request for proposal in Japanese, and maybe people can do a better job of that. RFP is request for proposal. Okay, I think it's gone past 1 here. What I'm going to do, right, is I'll look through your comments. So thank you for everyone who's participated tonight. Fantastic. I will look through your comments, and maybe I will announce a Q&A once I've done a bit of work tidying up the references and some of the data for this presentation during the week. I'll maybe do a Q&A on Zoom, and you can all kind of like ask questions directly, and rather than having too much Q&A bogging down the end of this presentation. So thanks, Slobodan. Yeah, fantastic talking to you in the week. I think we have a chance to. Yeah, I mean, you've been doing this research now for what, 17 years. So you've lived and breathed this stuff. In fact, actually, in his ICCF 22 presentation, go and look at it, because he shows these glowing balls under the very high ND filter. These glowing balls, and they're not just glowing and burning. They're glowing, and then they jump and relocate themselves, and they look exactly like the kind of balls that we see on the Vega experiments, where they kind of go here and then they maybe jump over here. You can see exactly the same thing, and I believe it is exactly the same thing. There's slightly different elements in there, but when you get down to it, it's all energy, it's all sound, it's all vibration, so it's all exactly the same thing. Can I show my invention on alternators? Fantastic. Yeah, W. Yeah, well, let's do that. Let's do that on the stream. Okay. Yeah, so I think we've got something. WP for Truth is going to show some invention, so that would be nice. And we'll have Q&A. Okay, so I'm going to call it a night. Thank you, guys. That was Tree of Life Part 2. I'll just do a quick run through of the presentation. There will be lots of material missed. But anyway, just the basic slides. So here we go. I started the presentation by talking about Kepri and how this looks like the embodiments of Evo production systems by Ken Shoulders and later by Lockheed Martin in their coherent matter wave patent. And the fact that the vibrating chitin on the shell here can, just like the chitin in cat's hair, be a good source of static electricity. The static electricity would be cohered by the vibration and the point emission from these structures. I talked about the fact that the hexagons cell structure on the back of the inside shell of the wing shells are probably the reason why this goes up, down, up, down, up, down, because it's just a kind of faux perspective, and that this will create the black sun or exotic vacuum object structure that's able to manipulate matter and do all kinds of funky stuff that we've talked about on this channel, and that the energy that comes for that it comes from spirit. It's actually etheric spirit energy. Through here, there's various names for that. You can call it chi and well, all the usual stuff, but it's etheric energy, spirit energy. I talked about the production of sulfur from leftover plasmoids. The reason I did this was to tie in with Slobodan Stankovic's work, where he saw the production of sulfur that wasn't in his system. There's no sulfur in this system. And also the fact that he had balls that were eating around his diamond-like layered, multi-layered crystallite structures, and I imagine that those were kind of like little leftovers of exotic vacuum objects from the main plasmoid that did the work in here, and that did the work in here, and then operated in this area. And in the same way, there were some structures that were left over on his diamond multi-layered structures. I then talked about this event with the carbon fluorine polymer, PTFE, the exposed titanium to Ohmasa gas, and how an explosive event caused instantaneous production of crystals within a boundary, and that boundary had the crystals with voids in it, just like was in the description in the 1992 Solin patent. And then looking into this, we had alpha conjugate nuclei on these spikes that come off in a regular sort of electromagnetic type of arrangement on these convex points. And I explained the element synthesis there that's going on with the alpha conjugate nuclei. I then looked at the thorium doped tungsten This is the raw material. In fact, this is the raw material on the sample that was exposed, but this is an area that's not exposed, and showed that it had some small amount of carbon and oxygen in there at the surface. It had the thorium, and that's basically the constitution of it. This is the experiment with Dr. George Eagley holding the vacuum cleaner, and he has a filter here where this was my design experiment to deal with critics that say it's always contamination on the sample. I thought, if it's contamination here, how do we if we can capture the fumes, which I saw coming off on various different experiments by these kind of technologies, do the fumes have the same material in there, and is it also including the elements that are synthesized? And sure enough, we see these channels just like we see in Slobodan Stankovic's work, and also that we see on the Vega Valley sample with these endpoints. With these structures in here, and when you look at those endpoints, you get the synthesized elements, just like the snowballs on cobblestones, and that in every case you get calcium. And when you want to know what's going on with calcium, well, if you fission tungsten isotopes, the 180 is very rare isotope in tungsten, but 182 and 184 account for 57%. The 184 and 182, they fission to calcium isotopes and xenon. And so these are very much larger atomic nuclei than the tungsten that they come from. So this would explain why they smash through the surface and do the damage that they do, dustifying the material. And so I looked at large areas, again, calcium everywhere, and all of the elements that Slobodan Stankovic has seen, and that we also see later and in other experiments talked about in the presentation and in other work. Classic hexagon structures on the tungsten, as well as the pretzel, which I found on many, many systems, and we are able to replicate, I believe, very simply in ultra experiments. And then there's the third one here, which I will talk about this particular cluster formation in the future, and I think this is absolutely stunning. What's the information that's conveyed in these formations, which we've replicated in the ultra experiments, but we'll talk about them another time. But specifically, it was this carbon film that comes out of this one. There's carbon film over here as well, and there's all these other elements, as you can see, and the actual elements, they follow specific areas in here. So I believe this is compression and decompression of the ether, and this leads to atomic nuclear reorganization and transmutation and synthesis and rebirth and conversion back to etheric energy. But anyway, this is the kind of thing here, and you basically see calcium everywhere. And calcium, as I've said before, it's double magic. It's 20 neutrons, 20 protons, and it has it's dec alpha, 10 alpha particles, and this is a really good element to be a basis for understanding LENR. And then I looked at the filter, and you can see the filter fibers here. The filter fiber 1230 is essentially just carbon with a very small carbon and oxygen here, whereas all the fragments that are caught in the filter are basically the same elemental compositions as we see here that we observed being synthesized on the tungsten. And for me, this is 100% proof, and this experiment type could be conducted by anyone with this kind of family of technology who has access to an SEM, probably with the SEM analysis in a morning or an afternoon. So there's literally no excuse for pretending that low energy nuclear reactions can't instantly be created. And so this was with the indium. This was the opposite scale. So we've had tungsten, the highest melting point metal. I think so that's the highest melting point metal. Later we talked about carbon, that's the highest melting point non-metal, and I chose the lowest melting point metal that didn't auto-ignite or ignite in contact with air or at elevated temperatures. And we showed that this produced a jelly-like state that was very similar to that produced by John Hutchison, and that is very interesting because it has a melting point that's above the highest assessed melting flame temperature of HHO gas, it didn't appear to melt, but it did turn to kind of like a jelly state. And then I showed this what looked like the formation of indium nitride on here. But even as that indium nitride is forming, it's still flapping around in the breeze like it's a piece of jelly, despite the fact it's the thickness of a human hair. But indium nitride is glowing at least, I would say, 1,000 to 1,100 degrees centigrade. What you're seeing here looks impossible. I mean, it may be carbon that's being synthesized here, and the carbon is glowing, but even then it's still a high temperature, relatively speaking, especially considering that this is changed its aperture down. So then I showed various eruptions and the eruption morphologies with what I believe is an ejection of indium plasma or indium gas, at least, that instantaneously oxidizes into these beautiful octahedral crystals. And then following on behind that, you get these eruptions of various elements, which are all of the elements that Matsumoto observed, but also that were observed in the tungsten and that were observed in the work of Slobodan Stankovic when he was just using carbon. And there's another example here. This is carbon film, and I was going to put the data there, but I didn't. But this is literally, there is a paper by Takaaki Matsumoto where he does a drawing of one of these carbon films all folded up like a transparent bed sheet. And it's almost, this could be the picture that he used for his sketch. Anyway, there we go. And we've got some other examples here. This is some data which I didn't show you, but I'll show you another time. But it's basically the same thing. You can see all the elements here. These are all the elements that you get in these systems. And this is a map of those elements in this very, very dynamic eruption. And then I talked about the conclusion that Ohmasa vibrator can transmute things, and Ohmasa gas is basically instant Lena. And so that was that, and I talked about the scarab beetle. So thank you very, very much, guys. I think that's it. So I shall see you anon another day. Bye-bye.